welcome you all to this afternoon.
You can take it closer. Closer.
Industry
Yes,
4.5
closer.
in sustainable trade technology. So this topic that we are going to cover today is about tracking digital twin. Overall, we have seen a lot of interest in this particular area, both in academia as well as in industries in the recent years, like last 1 to 2 years is what I can say. So, have you heard about this topic called digital twin? Anyone here already working in this particular area of digital twin? Anyone working? Not yet. So it's a new topic, right? So probably we'll be learning more about it today. So there is an interesting parallel I found to this topic very recently. So have you seen nowadays there are watches that are coming and that sort of track your body battery. Anybody aware of this? Let me see if you are able to find parallel from this perspective. There are watches that are coming which track your body battery. So they say this term body battery. Garmin has used this term, I know of. Anyone have heard this term? So the interesting thing is that what it does is that it tracks your movements, so it knows how much movement you are making in a day. What it also does is it tracks your heart levels. It tracks your heart rate variability, and essentially it finds out how much stress you are taking, how much rest you are getting. And it is able to calculate how much energy you have at a particular time in the day. So if you look from the parallel perspective, it's like it's creating a digital twin. Taking data from yourself, it's creating sort of like a digital twin, and using the twin is predicting how much energy you have in a particular part of the day, depending upon how your day is progressing. Right? So this is something that is gaining a lot of prominence nowadays because it gives us some very good insights. It allows us to optimize how we go about our day, right? If you are able to know how much energy you have accordingly, you can plan activities. So, digital twin is something that a lot of industries are now looking at. And to get a better insight into this particular technological area, we will pick up a particular example that we will use to understand more. So we will talk about digital twin of a battery. So here you can see just like a representation. So there is a person who is sitting somewhere and he is taking data from the cloud, and there is some asset somewhere, maybe a battery pack which is sending some data to the cloud. And from that data, we get certain insights, and those insights can be changing as we have more and more data coming in. So that is how the entire sort of process is. So, what are some of the key areas where you see MATLAB and Simulink being used? So obviously, I'm coming from MathWorks. So I think last day we had Dr. Shobik who sort of gave an overview about how MathWorks tools are used in different industries. So you can see that aerospace and automotive are major customers, but we have a wide range of industries that use these tools. So the other thing that is there also is that if you look at the different industry segments, you see that all of them are employing resources to gather data. So we have this industries are having resources which collect data. So and they are all interconnected. So we have a growth in smart connected system across many industries. So many industries use this. So now when we look at user stories of digital twin, we have some interesting examples that I would sort of show you. So one of them has sort of been covered yesterday, I believe. So before going to the user stories, what is a digital twin? So what we saw is that there is an asset which is there, which could be located anywhere, and from that asset, what we are trying to do is that we create a sort of representation of the particular asset which is updated based on how data comes in. So there is an actual physical system. From that physical system, we have data that comes in, and using that data, we have a model which is updated, and that provides us a up-to-date representation. So this will help us get an idea about the current state of the particular system, but also, since we have past data, we will have a historical idea also about how that asset performed in the past. So we have timestamp of that how the asset is performing over the past period also, based on from where we have started to collect that data. And the way we can go about using this data is that we can take that data, understand how the asset is functioning in the current time, and as we know, we are very interested in what is happening in the future, right? What will happen in the future. So we will use that data to make some predictions. Also, in many cases, we would like to optimize how the system is behaving. If there is a controls related to the system, we'll also try to see how we can refine the controls and have better performance out of it. So this is like sort of the definition we go by when it comes to a digital twin. So now we can relate to the two examples that we talked about. Like, the first example, like how the companies are taking data and getting a up-to-date representation about how your body energy levels are. Right? Any other examples you can think of where you think this term can come, a digital twin? Any other example where you think something like this could be useful?
Electric vehicles.
Definitely. Electric vehicles, they are actually looking at, I was recently reading that in the future, the cars will have algorithms that will sort of taking data from your driving style and accordingly it will get tuned so that it will give you the best performance for your individual driving style. So that's a good point. So that is from one segment, it's automotive. Okay. Any other segment? Yeah, that whole picture of multiple. So that's a very good example. Thank you, ma'am. So you have followed what Shaulik talked about yesterday. So when it comes to energy management of buildings, there also the concept of digital twin is very useful. Okay, so you will have an idea about what are the different places where you are spending energy, how much energy you can generate from a building, and sort of optimize the overall usage and have better efficiency. Okay. So let's look at a few other interesting user stories also. So there is a company called Schindler. Have you heard of this name, Schindler? So they make elevators. So what they do is that you can't always go and just commission an elevator like that, right? So they do virtual commissioning of elevators. So they have a digital twin of the elevator, and they get that data and perform virtual commissioning for those elevators. We have seen a lot of examples also from the mechanical domain. So people take systems like a pump, like pneumatic compression systems, wind turbine. So those are systems where people are also sort of trying to build a digital representation of that. And over a period of time, they try to see how they can accurately represent the real functioning of the system using data. So building IQ was the other example that Madam just mentioned. We see a lot of examples also in the aerospace domain. So aircraft companies, what they want to do is that they will have massive fleets. So they want to optimize and predict how the whole fleet performance is going to be. So Lockheed is actually using the digital twin concept to do this sort of tasks. At university, we have one example, like Korea Institute actually uses a digital twin for sort of identifying if there are any issues while manufacturing chips. Right? So semiconductor is now a very major source of industry which is looking at this sort of technology. So they use self-diagnosing. So they will identify whether chip is faulty or whether chip is fine. So they are creating a digital twin for that also. Electric vehicles we already saw, so that's also one very common area where we see a lot of influence. So what are the things why people are looking at? So overall, looking at the sort of use cases, we find that industries are actually using this digital twin. Some of the reasons being to find anomalies. If there is any fault in a particular system, so they should be able to identify that and find out what is causing that anomaly. Predicting maintenance, identifying whether thing is going to be faulty in the future or whether thing is going to need maintenance. So that is a very important area. Asset performance management. So there are companies like oil companies, there are companies like process industries, which might have a lot of different assets which should be functioning at a particular period of time. So they use data to understand all these performances of the different assets which are there at the given time. Operations optimization, fleet management, getting feedback with respect to the entire design process. So these are some of the things that are there from the use case perspective. What about the business thing? From the business perspective, do you think is there any benefit from the business perspective side of things with the digital twin? Performance, we understand. We understand that they would be able to identify faults earlier. You get good feedback. But what about money? In the end, people are also interested about money. So it's in the slide only. So as of now, the way business works is that we sell a system. So I sell you an electric car. Okay, it's done. You go and start using the car. But as a company, I'm not making any additional revenue out of it. But with a digital twin, you can also sell services. Maybe you can sell a software which will give you some insights about your particular car, some customization based on how you are driving. So they can not just sell a system, they will be able to sell additional services out of it. I'm not sure how many are aware, but there are companies in India which create digital twin of system, and they have customers sitting outside abroad who send their data to the system and sort of get insights out of it. So they are selling services, they don't have the asset at their side also. All they are selling is services. So this is a new domain, a new opportunity which has come up because of this area of digital twin. So this has made it possible to sell services also. Now comes to the part which is interesting, is that, so how do I go about designing a digital twin? Okay. So again, it's not a straightforward thing. There are many different we can go about it. So you know in MATLAB and Simulink there are so many different modeling paradigms. So you can use the appropriate modeling paradigm when it comes to a digital twin. So let's say you're creating digital twin of a pump. So how can you go about that? So pump you know is a physical system. Okay, if you know the behavior of the pump, so you can go with a physics-based model. Let's say you are working with any other system. So typically the system that you find where you can use a physics-based approach, these are multi-domain sort of systems. So you can use appropriate tools to model this sort of systems. Okay. So, and then there are systems where you don't have the equations known well, where you have to go for data, so then you can go with a data-driven system. So that is also there. And then nowadays it's very popular. So when you have a lot of data, then it's very interesting. You can actually try out AI-based systems also. Right? So there is machine learning, deep learning, reinforcement learning. These are all methods we can actually use. For data-driven, we have carbon estimator, there is system identification, regression. So it will totally depend upon what application we are going for. It will also depend upon how well we know the particular system, whether we have any past knowledge about any data from the system or we have just started gathering data. Also, it also depends upon what sort of expertise I have at my end. So if I am not very confident about a particular approach, It's better that I do not go with a particular approach. So this is how the entire modeling paradigm is there. So let's say we talk about a battery. Can you guess what sort of modeling paradigm we should go with? How many of you have modeled a battery before? Okay, sir has modeled. Anyone else? Okay, then there is one question that should go with this before we go ahead. Why should we model a battery? Do we need to model a battery? That is definitely there. So we want to know the battery characteristics that will come from the data. But why modeling? So we are looking more from technology. What about user perspective? All of you are users of battery, right? Laptop you have used, mobile you have used. What worries you most about a battery?
Charging.
Exactly. So there is an interesting thing. When you see the mobile charge going down, your anxiety goes up. Okay. Because we are worrying when you can next recharge the mobile. Similar, you can think of the same thing analogy. Take an electric vehicle. Anyone of you have an electric vehicle? That's great. That's pretty good. Vehicle has actually used methods tools for designing a particular vehicle. Okay. So I have an Hero Electric. Okay. It has a very, its rating is not that high. One single charge it goes about 40 kilometers. But if the charge goes somewhere around 30 to 40%, I can't come out of my office desk. It doesn't have the power, right? So we should be able to predict the state of charge of that particular battery. So it's very important that we should be able to predict the state of charge of the battery correctly. So you will see there are in certain phones you will have the battery go, let's say, very linearly up to 30%, and then it will fall very suddenly. Right? So the algorithm is not doing a very good job predicting the percentage, the state of charge of the battery. So that is a very good point. What other reasons to model a battery? So from a user perspective again. Okay, so that's again coming from the technology side, from user side. Overheating. Yes, that's a very good point. Overheating, right? So again, when you go as a user to buy a particular battery pack, we want to ensure that there are no incidents involved when you use that battery pack. And if you talk to people who sell electric cars, you will see that many are actually not adopting this sort of technology because they are worried that there could be a safety issue. Very interestingly, I came to know recently at a battery-related seminar held at IIT Roorkee that prior to I think 2023, India did not have a particular standard when it comes to battery safety. Anyone aware of this?
Yes.
So we had batteries in the field which did not adhere to certain standards. Those were imported. People just assembled them, started using them, and you have seen the result in the newspaper, right? So battery is a very key component where safety is of very paramount importance. So you should be able to model the battery in such a way that you understand that during charging and discharging cycles, what sort of temperature it would be. What would happen if you operate a battery in Bangalore compared to what happened in somewhere like Rajasthan, let's say, or in Ladakh? The reverse might happen, right? Your car will not start if the temperature is very low. So these are points that we have to keep in mind, and depending upon what we are trying to study, accordingly we have to choose which sort of modeling approach is useful. So let's say you are modeling a battery from safety perspective. So definitely you have to have a very good thermal model, detailed thermal model that you use for the simulation. Okay. So now you've done the thermal study, you know the battery is safe, you want to test the performance of the car. Will you use the same model? Why not? So when you want to find how the battery performance with respect to a car. Then you have to connect that battery model with the motor model, with the vehicle model, attach a drive cycle, then run simulations with the system level model. If you have a very detailed representation of the battery, you will see that you just sit there for a very long period before you get any result. System level model will take a lot of resources to run, longer run time. So there you might go for any other approach. So we have seen that if you want to sort of compromise slightly with respect to accuracy in the result, then go with an AI-based one or a data-driven one model for the battery. So we know that depending upon what sort of thing we are trying to study, what application we have, accordingly the model paradigm is going to change. So this is also very interesting. Again, if you have something like a digital twin, this is something like a representation in time, right? So how fast do you think you should update that digital twin? How fast? Exactly. Definitely you'll be very happy if you can do it real time. What thing else? So let's say if you have a digital twin somewhere, it has to get the data first. So at what rate are you capturing the data? You can't have a system and update it faster than at the rate at which you acquire data. Even with data coming in, right away you just can't use those data values to update. It will have some noise. So you have to do a bit of signal filtering, or you can say signal buffering that has to be there. So there are some interesting things that come up when you want to actually implement. The other things also, like how you are bringing the data. There are so many different protocols which are there which allow you to send data to the cloud and take data from the cloud to your digital twin. So it will depend upon those protocols also. And also, it's very interesting is that we should understand what data is relevant for our system. We do not want to have a lot of data and then later on try to filter it. So we should identify what data is relevant for the application and only use that to update. And then you can see this thing also, like so typically people will also have certain requests that you want to put in, right? You want to have a particular thing that you want at a particular point in time. So you do not need to always run this analysis in the background. So at an exact moment when you have that requirement, you run the analysis and get the result. So there is a request here, and then we have the entire model there, and we use the digital twin for a particular application, and then we send the response to the person. So we do not need to always keep the algorithm running in the background. So that is also there, specifically when it comes to use. Now placement we were talking about right now, just thinking from the cloud perspective, but when it comes to implementation, it could be placed in different places. So specifically when it comes to something like this, an anomaly detection. Some manufacturing thing is going on somewhere. There is a camera which is taking an image and trying to identify the anomaly. So we can have embedded systems like, let's say, some Raspberry Pi, some NVIDIA Jetson, which is just there. And so in that cases, it would be like an embedded application. We could have different edge systems. This also in case of predictive maintenance and all we see. And specifically when it comes to cloud, when people are actually working with a lot of data, so fleet management, operations, optimization, this is where we sort of look at the placement for the digital tool. So overall from our discussion, okay, so these are some of the points to summarize. What are the things we should look at before we go to plan that whether we should go for a digital twin or what sort of method we should use. So multiple questions will come up. Right? So, any questions as of now?
This digital tool is a simulation model where real-time data is kept. Right?
Yes.
So, how about the performance primarily of simulation as well as a real-time battery? Will it be similar because in real-time it will be affected by several parameters.
So that will totally depend upon what I'm going to use it for. It will be won't be exactly like a real battery. And we don't want it to be exactly like a real battery. With purpose it will be purposely created. Right? We have it because we want to do something very specific with it. And we saw that it allows certain advantages compared to a real battery. So that's a good point. It's not exactly, it's never going to be exactly like a battery. It will be only as accurate as the model and the data you send to it. Anyone from the students? Anything from your side? So now that you know the concept of digital twin, any other application that comes to your mind? So think about your projects. You can think from that perspective also. Maybe you find something that sort of aligns with this. We have seen examples in robotics also. Like you have a robot arm moving, let's say, in a factory, and there will be something also at your end moving in environment, digital environment. Those are also examples of digital. So the last aspect is also very interesting, specifically when it comes to students. So who should be designing the algorithm? Who would be the person who will be working with the data access, and who will deploy the model and algorithm? So in industry, they would have personas who actually work on different aspects of a digital twin. It's not the same person who does everything, right? It's not possible. So they will have personas. So somebody with a data science background might be working in the data access part. Somebody who has a very good knowledge of the domain will be the person who will design that algorithm. So let's say you are from electrical background, you will be designing the algorithm, you collaborate with someone from data science background with respect to data access, and then there will be one person who has very good knowledge about embedded systems or different sort of deployment options who will actually help you deploy that model and algorithm. So who are the person who actually work on this sort of problems? So this is one use case we have. So as we mentioned, electric vehicle is a very important area where we have this sort of examples. So there is a company called Neo. So with that they have actually designed a cloud-based architecture, a digital twin for state of health estimation of a battery. So they have done it something like, so they might have a lot of electric vehicles, a fleet of electric vehicles. So for that entire fleet, if you see here, there is a vehicle data. So the vehicle data, they sort of use MATLAB and Simulink, and then they sort of take the data and store it at a place in the cloud. They have a model which does the analytics part, and using a Docker container, they have sort of plugged it to the cloud platform, and from that data, they sort of get different sort of vehicle insights, and that they are able to visualize using a visual interface. So some interesting things to note here is that if you look at the previous things, so they have actually worked with a cloud-based platform. The reasoning is that they have a fleet, so they have a lot of data here. Lastly, when you develop this sort of algorithms, let's say if you have developed something in MATLAB and Simulink, it may not be there in MATLAB and Simulink only. So you want that thing to that battery they are connecting into a vehicle powertrain. They are also modeling the vehicle dynamics. So when a vehicle is moving on the road, how it is moving, what is its driving, the dynamics of it, and then under different conditions, how the vehicle is going to perform. All of it is included in the vehicle simulation model. But battery analytics part of it, they have algorithms which estimate the state of health of the battery, and then also tries to predict it. So that is running in the cloud. And then whatever they have created as model, they have generated code out of it. So in the cloud, it might run on any other programming syntax. So they have generated the code, and they are giving simulation now as a service. So let's say there is somebody who wants to use this sort of data, so they can buy it as a service, and they can create different batch simulations, do the analysis, and you have very good dashboard where you can visualize and get insights from the data. So this is one application of a digital twin that we have seen in the industry, and they have used MATLAB and Simulink to do something like this. So let's look at the first example, and let's get an idea of, we will delve a bit deeper and try to see how you build this sort of model. Okay, and later on, during the hands-on part, we will be trying to run through an example and get an idea how we can go about it. So, example-wise, I have 3 examples, but depending upon time, we will find out how many we can actually do the hands-on with. But I will give you an idea what is there. So first, we will look at a very simple example of how you can model a battery. So with this we covered why physical models of batteries required. So what happens in a battery? How does it store charge? This we know, right? Why does the battery store charge? So yeah, so looking at from the very broad perspective, we are converting electric energy to chemical energy. Okay, and later on we are just incorporating it back. So internally, if you look, there are certain ions which move. Okay, from one electrode to the other, there is a movement of ions, and that allows us to store this charge in the particular battery. If you want to model a particular battery, one of the ways you can go about it is actually model the electrochemistry of the particular battery, because there is an electrochemical energy conversion. If you model the exact electrochemistry, you will find the performance of the battery. So that is possible. So that is the first one that you look at the very top. So battery will have an electrode, 2 electrodes, and an electrolyte. And then there are equations that come from the electrochemical domain, like Gauss equation. If you solve those equations, you will find out how the battery voltage changes with respect to flow of current. That is possible. It's a pretty detailed model. Typically, if you are actually very interested in understanding the battery behavior, you can go with this sort of model. In industries, we are fine typically going with something less computationally intensive. So we will look at the second approach which you see here, which is known as the equivalent circuit approach of modeling a battery. Equivalent circuit approach, why we come to this in the next step. And there is a third way also which is possible. So the third way is that, okay, I have, let's say, a lot of data at my side. I will use some sort of AI-based approach. I will use a machine learning model or a deep learning model to come up with the battery model. So that is also possible. It will be something less computationally intensive. So what will be my next step? So when it comes to a particular battery, so when it comes to a battery, study how the current changes with respect to voltage. What am I interested in? So I am interested in understanding the dynamics of a battery. Okay, remember this very well. I am interested in knowing the dynamics of a battery. Dynamics means that when you draw a current from a battery, its voltage will change, but under different conditions also it will change. So it's a very dynamic sort of a behavior. Okay, the load will also change dynamically. It's a very dynamic sort of a system. We want to capture that. So how is it possible to do that? What we are doing here is that we are creating a physical representation of the battery just using electric circuit. Just by putting some electrical elements like capacitors, a source, a resistor, we will sort of have the so in this circuit, if you create a circuit like this, what we expect is that if you draw current on the circuit dynamically, it should reflect how the battery is going to actually behave in the dynamic condition. So this is also you can think of like something that actually mimics the battery. Okay, it will mimic the behavior of the battery. So we are trying to create something like that. So to go about doing something like this, we need to know the parameter values of all these different components in the circuit, and we have to make a circuit like this also. So there are all these components which are there. And all of these components are not just fixed values, they will have dependence. In the case of a battery, depending upon what is the state of charge of the battery, the parameter values are all going to change. They all have dependence upon the state of charge of the battery as well as the temperature of the battery also. So this is a task that we have at hand. How can you build something like this in MATLAB basically? Shall we give you some idea of it? So here it is like a hash code, SimScape. So actually you can do it in any given environment also. You can create these models in MATLAB also. You can write the equations and model. It's not very convenient. You can do it in Simulink also. We know the behavior of the circuits and how V equal to IR, those terms, right? You can do it. For capacitors, we will be having that C dVdt. Those we can do. It is possible to do it in Simulink also. Not very convenient, but the easiest way to make the circuit is to use something known as SimScape. In SimScape, you just take this element, drag and drop on the canvas, and create a circuit. So we'll see how this happens during the hands-on part. So you can create this physical sort of a representation very easily. We can also have, so there are also blocks that come in SimScape where you don't ever have to connect each and every circuit component and do. They will have a built-in block, you parameterize it, and you can start using it. So everything is actually having an equation. Okay, so as I mentioned, everything has an equation. It's not like a black box way connecting. These are all physical models. So in terms of the whole modeling paradigm, this is a physical way of modeling. Equation-based approach or first principles. This is how this approach goes. What is interesting now is that we have the circuit. What values will you give here for the resistor, for the capacitor, for the resistance? What is the value you give? Or how will you give the values? Mathematical model is there. Parameter values. So man is saying equations for.
It's designed equation like KVL equation, circuit, right equation, will have constant values.
So that is what SimScape will do for you. So if you solve those algebraic, the differential algebraic equations, it will come out based on the connections. So SimScape will solve, but it will ask you what is resistance value, what is capacitance value, what is the these parameters? How will you keep those parameters?
We are taking some papers and that's the specification or our own design papers.
That's correct. So, like what ma'am said, that is also true. You have some paper. Typically, papers will also not give you the data. So, there are battery manufacturers which give you the data sheet. So, the data sheet is in the form of tables. You take those tables and parameterize this block. So, typically, they will not give you individually for a resistor and capacitor. They will not give you. They will give you something different. Okay, so they will give you something like a time constant tau, R1 into C1. This value will give. Okay. So these are parameters which you can get either in the data set as sir mentioned. So if you are using battery from a known manufacturer, you will get this data set. So you can ask them, they will give you the data set. You parameterize and you can start using the model. The other thing comes up is that you don't have the data set. You are working with someone who has given you a battery and says that okay, I have the battery. This is not a chemical composition is found in the market. This is something I have built. So now what to do? So then you need data to be collected from there. That data we can use. Okay. So the interesting thing is that data, one of the popular ones is known as a pulse discharge. Come back to it later. So what essentially happens is that there is a pulse discharge. They will take your battery, they will connect it to a system which will apply certain loads that will draw a current at certain points in time. So at a certain point in time, there is a current pulse withdrawn from the battery, then it stops, comes back. Current pulse drawn, withdraws, comes back. So exactly we will have something like this. What we will measure here, voltage we will measure. And the voltage, if you look, it has a certain pattern to it. It does not exactly correspond to what you see in the. So you are giving an excitation, right? You are drawing current at a certain point in time. The voltage curve, if you see, it does not follow the same pattern. It has a certain pattern that is very distinct. And there is a reason you get this pattern. This pattern in the voltage response is because of the dynamics of the battery. So we want to know the dynamics of the battery. If you do this particular experiment known as pulse discharge, you will get the data at your end, the voltage response you will get. And this voltage response, if you study very closely, it will tell you something. So it has these components, right? So this is the voltage discharge. At a certain point in time, when there was a pulse, current pulse withdrawn, the voltage is having a response like this. So immediately when you start drawing the particular current, it falls rapidly down. And then when you stop drawing, and when you sort of, so here if you see there is a slope, and when you stop drawing current, again there is a slope. So immediately it does not follow the current response, it takes some time to come back. So what is interesting about this? The instantaneous response here, if you look at the instantaneous response, this will give you the value for the resistance that you see here, R0. So it is a resistive sort of behavior that we are able to capture from this part of the curve. Why resistive? Because if you look at electron movement, it's very fast. Okay, so resistive part, instantaneously you see the result. And then there is a delayed response. It takes some time to come up. Why is that? Think of it physically. Why is there a delay here? It takes some time to get to the original value. Why is that? So it is related to this branch, this R1C1 branch. So if you are from electrical domain, you know that when you have a circuit with charges and discharges, you will have this sort of a behavior from where you find the time constant. What phenomenon corresponds to this? There is something that is happening inside the battery because of which you have this delay. One part of it you are able to capture very fast, electron movement. Why this? There is something that is causing this to take some time. Wow. What phenomenon is that? One is because of the electron movement. What is the other? So that takes some time, so that because of that you have a response like this. Okay, it takes some time. So if you want to model it specifically from the perspective of from the chemical part of it, you have to model those behavior those transport behavior you have to model accurately to capture battery dynamics, right? But if you go look from the equivalent circuit approach of it, same phenomena we are trying to capture just by using electrical elements. Same phenomena. So this is how you get an equivalent circuit. So given this data, if I give you this data, then you can find these parameters also. You do not have to go to a manufacturer. There is a process that is involved there that will give you these parameters. So for an unknown battery, we find these parameters, okay, and we will get something like tables like this. And we will be getting these values in the tables also. So this is what we are going to get in the very end. So we will be doing this exercise. So this will be the data here, the measured data, and I will have the model also. So the electrical model I will build in Simscape. I will have the measured data, and I will find these particular parameters. So this process is actually uses something in Simulink known as Simulink design optimization. And in the end, it will give me a table of data that I have. So iteratively, so here it is just represented iteratively, it will run the simulation in the backend, and it will optimize so that the output of the model matches the experimental result. So this is the example from Simulink. It is running in Simulink. We will run it in a script later, but this is how this particular thing looks. So here if you see, I will have a lithium cell. Okay, so this is the equivalent circuit that we have built here. It is like a lithium cell. I am sensing the voltage. There is a current source where I am putting the current pulses. So the pulses we are putting. So we are drawing a certain amount of current at a point in time, and we are sensing the voltage across it. What I am also doing is that I am going to use something known as the Simulink design optimization to find the parameters of this model. Right now, the parameters that are there here, their value is just case value, it's not correct. So we will use Simulink design optimization to find the parameters of this particular model. So we will go, if you just run it, you will see that you will get some response. Okay, and it doesn't match. There is an experimental data, and you see there is simulated data also, they do not match with. So there is something like this known as parameter estimator. Here we have to go, give the data here. It's writing what the data is. I think so here we are just passing in the data, and then what we also do, so you can see the data here also, voltage and current. We also decide what is the input signal. So input signal will be the pulse discharge. And then what we do, we also want to look at the output. So we have just found plotted the curves here. So here we start some experiment, and then here I think we will identify the parameters also. So for parameters that are going to be useful for us is R0, R1 and C1. So first we create an experiment. So this is just an idea. So you don't have to copy any of the steps. We have the steps properly given. So you can just look at, you can use this sort of a environment to actually do the parameter estimation. Is it visible anywhere from the back? I don't think so. Okay, then I will just let it pass. So overall, you see there are some parameters that I have identified from my model, and then what this interface actually does is that based on the parameters, it will run an optimization in the background, change the parameters each time in the simulation, and then compare between the measured and the simulation output, and then try to match it. When it matches, I know that okay, it has identified the parameters. And this we do for different temperatures, this we do for different SOCs. The only good thing is that it can be automated, so I don't have to sit and do for all different temperatures and SOCs. It can be automated, it will run in the background like this, and all the parameters will be found out with respect to temperature and SOC. So there is a way of doing it in Simulink, there is a way of doing it also from MATLAB. Should I show the MATLAB or not? The hands-on part I can show in the lab also. In the lab I can show it. Yeah. So basically it does, what it does is that in the background it will change this parameter and identify the minima there. So whenever you have curves like this, there will be an error, right? So it tries to just minimize the error, and you have to give it certain initialization condition. So the hands-on example will come to it in the next step. Other things are that what people are also very much interested in is, so this will sort of allow us to create a digital representation of a battery. How? So what we have learned now, this will give me the parameters in the very end. So this will allow us to have a digital twin of a battery. How? So this will be right now, right? I had data. So this thing, if you sort of take the process, the algorithm, and if you run it in the cloud, and if you have data streaming in, this will create a battery twin which will get updated, and this optimization will run at certain points in time, and it will give you the parameters, so you will know how the battery is sort of functioning. So these parameters will allow you to have a digital twin of the battery. So it's possible. Any questions on this? And just not for this, like what we have learned for the battery, it can be extended to any other system also. Any other system, if you are able to create a physical representation of that, like of that in Simscape or Simulink, you can have data streaming in Simulink, and then you can update those parameters at certain points in time, and you will have a snapshot of the system at certain points in time also. So that will be the digital twin for that particular system. I'm not going to the communication part of it, but there is a communication element also, like how will you get the data into MATLAB, whether it is your physical MATLAB or in the cloud. But there is a toolbox which is there known as industrial communication toolbox. It will allow you to actually bring in data from different systems. Or there is ThinkSpeak also, the cloud platform that we have where you can keep data and stream data to your MATLAB or any other place. So that is the other part which is there. So what we see is that many users are actually looking at how they can update the battery model parameter and then get the state of charge of the battery or state of health of the battery during operation. So this is how the whole digital twin is going to be, right? So at certain points in time, we will update that particular system, and if we tune the parameter at those times, sort of it will be like a digital twin at that point in time. Okay, so what we want to do at a certain point now, if you want to find how it is at a certain point in time, we will be updating using the data that is streaming in. Okay, so this happens for every single digital twin. So if you have a large twin, you have to do it for every physical system which is there. Right. Now, when it comes to updating these parameters, there are two ways one can go about it. One is what we were talking about. One could be something like data streaming in, and then we are doing this process. The other could also be like a batch sort of system. So batch means a batch of data comes in, and we use that batch of data to update that particular system. This people actually use specifically when it comes system level model. So you have a very big model, you don't want to do data updation very fast. So there we do this sort of tuning as a batch operation. Okay. It needs a lot of compute power, and in this case we also need to define at what certain points in time we are interested in updating that particular system. There are also other estimations which are, I would say, comparatively less computation intensive. So in those cases, we can do online parameter estimation also. So here we can use methods like carbon filters. Specifically here, only few critical parameters we look at for the tuning part. Okay, and model updation actually can be happening at regular intervals. So it's quite, I would say, continuous in terms of estimation. So before going ahead, are you aware of this thing, carbon filtering? How many of you are aware of this? Or have used this? Anyone else who has used this? In control is digital knowledge. Digital signal processing also. So here, actually the system is modeled in terms of states. So states, you understand? States. I think there was a very an easy thing of state is like a system which goes from one state to another state. Like a very simple quadratic like charge state and then like discharging state. Right? Or let's say a rocket. A rocket is there on the launch pad. Then it takes or it flies. Then it reaches a certain constant velocity. So there are certain states of the system. So we try to model the system in terms of certain states. So here also there is a model. And the model is exactly like the equivalent circuit that we have seen before. So what here we do is that there are two things. There is a time update. So there is a prediction part. We sort of try to predict how the system is going to be at the next time step by doing some sort of projection. Okay. So there is a projection and it is based upon some sort of error estimation. So there is an error covariance which is there. We are estimating, and at the same time we are also measuring. Right? So in case of a battery configuration, we measure the voltage. So we are predicting and we are measuring the voltage. So there is an estimation that happens. And in this case of estimation, we incorporate a new measurement, and using that sort of identify the particular state of the system. So it's a two-stage process. So just it's good to know this much only that it's a two-stage process, and this will allow you to determine the state of charge of the battery. This is used to determine state of charge of the battery, state of health of the battery. By the way, are you aware the state of charge of a battery cannot be directly measured? Are you aware of that?
Yes, sir.
Why is that? So whatever you see in your mobile phone, the state of charge that it shows you, 80%, 55%, or any other value, it is not something, I would say, concrete. It totally depends upon the algorithm that is running in your mobile. Are you aware of this? Or do you think, or do you believe that what it shows is actually very correct? Do you believe it to be totally correct? Why is that? Why can't we measure the state of charge of the battery?
The measure based on the voltage based on the voltage levels of batteries.
Voltage?
Levels of batteries. Present voltage level of batteries based on say give some algorithms. If it is of this percentage or this voltage is in this percentage.
Yeah. So definition was used correct. So what they are measuring is like definition of state of charge is how much time it will get discharged to that particular value. But how do you know? So I will give you a very general example. You can imagine I have a bucket. Okay, I open water. Okay, I know at what time the bucket will fill up. Why do I know that? Because I am an observer. I chemical process, it can't be seen. So indirectly, we have to identify some parameter using which we can sort of indirectly estimate how much charge is there. Okay, so that is where these sort of algorithms are coming in. So the better the algorithm, the better accuracy you will sort of get. So Kalman filtering is something also, it is taking your battery and sort of looking at the whole battery in terms of states, and then it is making some predictions and it is also measuring something, and based upon those, it is identifying how the state of the charge of the battery is. So if you look in terms of the problem, we want to find the state of charge of the battery. So here also, given it's a state, there is a model behind that state. It's not like without models. The model is exactly what we have learned. There is an equivalent circuit which is there, and then we are using. So the good thing about MATLAB is that even though I'm not a very good, maybe, so I'm an engineer on the domain, but maybe I do not have a lot of experience building Kalman filters. So you just go to the control system toolbox, you have the Kalman filter. So specifically in case of the Kalman filter also, we are modeling the dynamics of the battery. So the equations are coming to the very top. We take the battery dynamic equations, we discretize the equations because we want to predict the battery performance at certain points in time. So we discretize the same equations in time, and then we estimate the initial covariance, process noise, and we do some measurements also. And from there we find out what is the state of charge of the battery. In case of MATLAB, the good thing is that we have this sort of estimators in the control system toolbox. You just bring it into your model, you pass it the battery state function. So here we are passing the battery state function. We are passing the covariance, the initial covariance. Okay. So this is the uncentered Kalman filter. And then once you run it, you will see that you will get something like this. So there are two curves actually. So there is something that says actual, but there is that estimation one also. So initially if you see, and here we are plotting the other thing, the difference between the real SOC and estimated SOC. So what we see here is that initially when it starts, there is quite a bit of departure. So here you can see there is some departure here. But then very quickly it is able to actually start estimating the SOC of the battery. And it has a very less error, 0.5% error. So if you have this sort of models, you can update it very fast. Okay. And then it is able to track also the state of charge of the battery. So this is something useful that you can use if you are building a battery digital twin, and that has to just give you the state of charge of the battery. So the example is there. So later on, if you want, we can open up this example and start running. What other options do we have? So there is a third option also, where we have something known as a neural network. So now we are looking at AI-based approaches. So in case of a neural network, what we want to do is that we have in this case a neural network, and we can train that neural network to predict the battery state of charge. So we have to give it certain inputs. So here if you see, I have given it 3 inputs: voltage, current, and temperature. Okay, so this data if we have, we can use that data and train that particular model. So I put here deep learning. So this is an AI-based method. It will allow me to predict the state of charge of the battery. Okay, internally it will sort of configure the model parameters in such a way that it will predict the state of charge of the battery. We will perhaps open this example, but we have a very nice video series also, which shows you the different steps. Okay. So it talks about how you can use this neural networks, what are this neural network. Okay, so this is an AI-based approach. So anyone here who is familiar with the AI-based approaches? Do you have a course on artificial intelligence? Students, are you aware of AI-based familiar with this? Or machine learning, deep learning? So no matter whether you're using machine learning or deep learning, either of these approaches is possible. You have the data, using the data you train the model, and then you identify the state of charge of the battery. I have not posted it here, but there is a company called KPIT you have heard in automotive domain, they have used an AI-based model to actually determine state of charge and health of the battery. So differentiating from what we have seen in case of the carbon filter approach, when do we go for this approach? An AI-based approach. When do you think we should go for this approach? So ma'am has a very good perspective. That's very correct. So in this case, if you see the AI-based model, if you there are so many different models which are there, but the good part about this is that they are very lightweight. Okay, so they are very easy to deploy, and if you want to have something that runs very close, so you can run something like a real-time system. So this would be the sort of approach that one can run. So there are automotive companies that actually use this sort of approaches. The reason being that any detailed model will take a longer time to run. So unless you are looking at something very specific, you can actually go for this sort of approaches. Any questions on this? Any questions? All good? So what is the state of charge of your battery now? So understand afternoon session is not very easy to follow when you have so much technical terms coming in. I don't know what is the time. Is it time? 3 days. Will you continue or do you want to have a break or something?
We'll wait for emails happening. Before going to the last session.
Okay, then we will have a break. Okay, then I will just go with the presentation.
Sir, no, only carbon filter algorithm only used for refining the expenses. Only carbon filter algorithm is used.
No, no, you can use this here.
Yes, this one only. So why specifically
Which one?
carbon filter?
It is one of the ways which you can do. And
Any other optimization algorithm can be used.
so carbon filter, there are different types of carbon filters which can be used. This one may be the one that I showed you on the one. I say adaptive carbon filter which people are using. So there are so many carbon filters that people use. Yes. Adam? Okay. Can you explain more?
Means it will reduce the efficiency of the battery. Means it will predict the efficiency of the battery.
Okay.
What other filters they use.
Okay. So that's a good point.
Basically, literature also they prefer only carbon filter.
So, so that is good in a way because you can sort of, so the algorithm part you can understand very well, right? So it gives you some insights. With AI model, the challenge is that often, so in industry, it's a very important thing also to go to explainability, how much you can explain how model is correct. So if you are very much interested in knowing how the thing is doing, then I think going with traditional methods is much more better. But AI-based approaches have also worked out well. So nowadays, what they do is that they will have initially a model, a very high fidelity model that will predict the sort of SOC and all. So they will take those sort of models and generate a lot of data. So when you have a lot of data, then you build an AI model. And that AI model is very easy to deploy because it has a very small size and all. So those they are also the sort of tools. So we have seen industry. So industry call this sort of approaches. Sometimes they call it the reduced order model. Reduced order means you are not using a very high fidelity model. You are reducing the order of the model and then deploying it. Runs very fast and it's good for. So the main challenge comes when you run large system models where you have a battery model. So if there is a need, I mean, when you're running the system model, you find that, okay, maybe here I can reduce the complexity at a certain cost. It will not be that accurate. So then you go for an AI-based model. That also works out. Here also there is a differentiation. People go for something like machine learning model or deep learning model. So those are also places where people are trying to experiment.
But for whatever you take the tree of the voltage, current, and temperature would be there and data sets.
So in terms of data sets, I think we have large data sets. In this case, the example that I have, I used only these three. But even here, I think there has been some sort of averaging that we have done. If I remember the example, has been some averaging which is done, gives us some additional data sets.
Generated through this primary data sets.
Yeah. So we have experimental data here from University of Waterloo, which was used to validate this particular model. So that way, we had access to the data. So having access to the data is a main thing. If you don't have access to data, then it's difficult to go with AI-based approaches actually. So also, like when it comes to data-driven approaches, people actually use data-driven approaches to estimate the remaining useful lifetime. So this is also where we see a lot of interest. So here if you see what we want to do is we have to predict how long a battery is sort of going to give a particular performance. So then the workflow that we will use is something that is very similar to what we do in the predictive maintenance workflow. So from the battery, we will get certain data. So we will have sensor data. And given that this is like coming already into the AI domain, what people also do is that after taking sensor data, we will do certain signal processing, or we can do additional simulation and we can generate some additional data also. So data acquiring is going to be the first part, and then we will pre-process that data. Then there is going to be a prediction model, so there will be a detection of prediction model. So this will again come into the purview of the AI part. Certain indicators we will select, and depending upon those indicators, so indicators for certain fault. Okay, if this fault happens, in the signal we are going to see something like this. So based on that, we will train a model, and then we will deploy that particular model. And as time goes, we will have more and more data. So we have the option of doing this iteratively and getting better and better at the predicting part capabilities.
So one thing, the Kalman filter was used for the pre-processing data part.
Which one?
Kalman filter that you were talking about. Is it used for the pre-processing of the data, or is it the entire complete?
So that is part of the digital twin of it. Pre-processing data here means that data will have certain inherent fluctuations, certain missing points. So that pre-processing part is what I'm talking about.
So this filtering is not part of pre-processing. The filtering that usually do in case of image processing or something like that, the Gaussian filtering or anything like that.
Yeah. So that filter we talk. So you are correct.
Kalman is there in there.
Kalman is part of the battery model.
Okay.
Yeah. That filtering is separate. So that you are correct. So that filtering is part of the pre-processing. So that's a good point.
How to create the digital twin of our Excite battery?
You have an Excite battery. And where is that located?
It's a car.
That's a good point. So first you have to measure certain characteristics of the battery. You have to have certain sensors. Very simply, like as I mentioned, the simplest thing you can do is measure voltage, current, temperature. Those three things if you measure, that data has to stream. So that data has to stream somewhere. So for that, either if there is some model in my car that can send data by Wi-Fi, I can send it to the cloud. Either simplest thing I can send it to the C-Speak, which is the cloud platform manager. And there I can create and deploy any algorithm in the cloud that will run the digital twin there and tell me how the battery is functioning. And if I want to take in my mobile, I can stream that data directly from the cloud. I can create a small app for my mobile itself and deploy it. And in my mobile, I can monitor it. So I like this. We should try these simple things and try out. I would say this could be a project that is in trial. So I have actually worked with a few university researchers in this particular area of battery digital twins. We have seen digital twin for wind turbines. So they had a actual wind turbine, and they wanted to create a digital twin of that to find out after what period of time would vibrations develop in the wind turbine. So very simple sort of sensors they had put, accelerometers, and those sort of things. So if you have any physical asset, you can create a digital representation of that, the digital twin of that, and try to see what are the things you can optimize and all. So typically the questions like these sort of questions is what people sort of come up when it comes to digital twin. So first thing, it's not always like predicting a fault, but many people are trying to see whether that machine is actually operating normally or not. So if the machine is behaving not in the correct way, what is that abnormality? Whether I'm able to figure it out or not. And specifically, how much longer I can operate before there will be some catastrophic failure. So first one, it is called anomaly detection. Second one, it is called condition monitoring. And third one is called really useful live estimation. So like for batteries, if it comes to batteries, so I have a battery, maybe the state of health is deteriorating very fast. So how can I know? So I have to monitor certain parameters. And typically what I want to do is that I want to predict that, okay, I can do 10 more charge cycles before it hits a replacement. And this is a very important problem, I would say. So as of now, in industry, this is a very major area where many are working. Because when it comes to the automotive companies, if you see, they are selling you car, they are giving you guarantee that the battery pack will last 8 years. You think they know that how much time it is going to last? It's not an easy thing. So I know there are multiple automotive companies which actually are working in this area very closely. They want to identify whether there is some fault in the battery pack. It's not an easy thing to do. So if you are a user, you will know. So it's not an easy thing to do. So they also want to predict that for let's say battery pack that has gone a certain period of time, how many times will you change it? Recharge it more before there is some failure. So here we look at using some sort of condition indicator. So typically condition indicator is something that will tell you whether there is some fault occurring or not. And that can help us to identify the unique useful life of the battery. So there will be some raw data like this. Okay. So I know for healthy operation there is something, a different sort of signature comes, and for faulty operation there is a different sort of signature which comes from the sensor that I have put on the particular asset. So we'll identify certain condition indicators, okay, and then based on the condition indicator we should be able to tell whether it is working properly or not. So something that helps us here is known as the diagnostic feature designer app. So I think Shauri covered the different apps which are there in MATLAB. This is one more app which is there, which you can access directly from the tools tree. And what it helps you do is that it allows you to extract, visualize, and rank different features from the sensor data. So once you have sensor data at your end, you can actually visualize all of them, and then try to identify what could be a good condition indicator of that particular fault. So it uses different sort of methods coming from the statistical background and different dynamic modeling backgrounds. So this could be an app that you can try out to identify this sort of signals. So I think we have one example here. So this is one example where we try to predict the remaining useful life of a battery. So how much long you can operate a particular battery. So let's say if you have a particular battery, depending upon what sort of signal you are having at your end, in time, you should be able to tell that, okay, if I have 100 discharges, I am somewhere here. After 500 cycles, I am somewhere here. After after let's say 1000 cycle, I am somewhere here. So this is going to be the remaining useful life of my battery. So we have a condition indicator. Based on the condition indicator, so there will be some signal which is the condition indicator. Based on that, there will be an algorithm that will estimate the remaining useful life of the battery. So this is where you actually go for the machine learning workflow. I will not go into the detail of it, but typically you start with data. You again have a model. You train that particular model based on the signals you have extracted. Specifically, the signal which has that particular condition indicator, and then that model you can deploy. That will sort of tell you this sort of things. And then you integrate it into the application part of it and do the prediction. So there are different sort of estimator models which are there, depending upon what I'm looking at. So there are models which are just look at something like, okay, is my battery healthy or is it going to be failure mode? There are survival models and then there are degradation models. So each one has their own performance, function. So we have this example. Maybe we will look at this later. So we have a lot of data. You can see here we have plotted capacity data of around 41 cell stack. So this is sort of the real data that we have at our end. And if you see here, one side of the axis is discharge capacity, and the other side is the cycle. So we can see specifically here, if you can see, like we have a lot of data points here accumulated. Right? So raw data we have sort of plotted here, and we can see the discharge difference in discharge capacity as a function of voltage. So as you have more and more cycles, you will see that the battery life, how it sort of degrades, will do this sort of estimation from this data. So this data we have to pre-process, train an algorithm, and then we can do this sort of processing. So I think in the interest of time, I'll let this thing be here. We will look at it more during the hands-on class. That will give us a much more better idea about what is happening. So overall, what we want to do here is that we will have some sort of asset from the data. We should be able to monitor that particular system, and here we should be able to give some sort of alarm that okay, this condition is occurring, maybe we need replacement, or maybe let's say this. So the second thing was could be something for an automotive, like if a truck has this much charge, maybe you can go this much distance only. Okay. So depending on what sort of application we have, we should be having some sort of output from that particular system at our end, so that we can take some action. So these people are now trying to sell us a service actually.
Sir, but these guys, I've seen laptop prediction is already there.
Which one?
Laptop, battery, this many hours it might take. That prediction is already there.
So that is for the algorithm which somebody has designed somewhere. It might not be that accurate also. Or let's say sometimes
For all the laptops we have that.
we have that.
Battery is training is this much, it might come for this many hours.
Correct,
It's already
correct.
there.
It's there, it's there. But it is
How
also.
is it applicable here? It can be implemented easily, right? So why?
Which one?
So these also, any applications that you're talking about, why isn't it implemented long? Because it is implemented in laptops, I think, maybe 5 years.
So laptop, if you see, even in laptop we have certain challenges also. So there will be laptops where it will show you something. Let's say after a longer period of time, if you see, it is not able to track it that accurately. So for older laptop, you have seen it will show like let's say 50%, 40%, 30%, and then it just goes on. So the algorithm also there is a place where it can be improved better. But laptop is an application where I would say it's not even that severe. Specifically in case of cars, but big stack, so many different cells. There could be so many other conditions which could happen. There could be a short circuit. There could be some part of the stack which has more temperature. There will be some part of the stack where maybe the coolant flow is not happening properly. Something or the other might happen, and that might cause some issue with that particular battery stack. In those cases, people are still working on finding out what would be a better algorithm. I know many people who have bought electric cars and they have to have battery cells replaced. They were not able to understand what caused the fault. So they had to take it to a service station. They were not able to understand what was causing the fault. They just tried to see, charge and discharge, and again take the car on the road, and then they are understanding that okay, something is happening. There is a fault. We have to replace the entire thing. And this is a big cost for the companies also. So they are trying to understand what could be a better way in which they can do this. Also, one more application where we hear a lot about is that for certain applications which are very critical, where let's say battery is the last option, battery is the backup. There could be some system, uh, some sort of communication system somewhere in the ocean, where when everything fails, they depend upon the battery. In those cases, they have to very accurately say that after how much time is that battery discharged. Okay, so that their operations are not hampered. In those cases also they are building digital tools. That's a good point. So overall, we had looked at from the very beginning what are digital tools, some examples of digital tools in this case. Then we took battery as an example and tried to identify what are the modeling methods you can use for a digital tool. We got an intro into how you can use a physical model using the equivalent approach and build a model for a battery, estimating the parameters of that particular digital tool. And then it also saw like what other ways are there. So we saw carbon filtering, so ways in which you can determine the state of charge of the battery, state of health of the battery during operation. And finally, the last part of thing, which I just breezed over, we have not gone into much detail, is how you can estimate the remaining life of the battery by using data-driven approaches. So we will go now, we'll take a break and then we will again join for the hands-on, where we will take a look at certain example and get a feel of how you can build a